Ba-ba-da-ba-ba-ba-da-bow. Work energy. Okay, so even though it is a wintry ice world outside, the Pirates naturally are going to have a bad baseball season, so might as well talk about some baseball. We have a 62-kilogram baseball player, and they hit the ball, they hit it into right field, it went into the corner. So they hit first, they hit second, they're going around, they're going for the triple. As they're approaching third base, they're told to slide, so they begin their slide with a speed of 4.4 meters per second. When you slide on dirt, it slows you down. If you've never experienced that, may I encourage you to put on a pair of shorts and then go run into your local baseball field and slide. You're gonna scrape your legs up like no tomorrow. I know this from personal experience. Picking pebbles out of your leg is never a fun time. Because there's this frictional force though, you are going to slow down so that when this player hits the bag, third base, they're only moving at 1.2 meters per second. What we would like to know is, how far from the base did this player begin their slide? Whew. Well, we can figure this out. We know, and let's just draw a picture here, that if this is third base, let's just draw the base right here. These don't have to be great drawings, but drawings are how we look at problems. We know initially they have some speed of 4.4 meters per second, and when they hit the bag, they're still moving at some final speed of 1.2 meters per second. And we're just trying to figure out, from here to here, what is this delta x? And we also know that over the entirety of their slide, they had a frictional force acting against them. Well, if they're moving, in this case, to the left, frictional force has to oppose that motion, so this friction has to be acting to the right. And this isn't the greatest free body diagram because technically these velocities shouldn't be drawn there. They should be drawn up here. But there is some frictional force slowing our ball player down. Okay? So they're moving to the left, and that force is acting to the right. So, if we think about our work energy equation, we know that some work is going to be equal to a change in kinetic energy. So, with our equation, F dot delta x, this is going to be equal to the 1/2 m final velocity squared minus 1/2 m the initial velocity squared. And if you wanted to, you could write it like this. You could factor out the 1/2 and the m and write vf squared minus vi squared. But be careful if you do that. You need to make sure you square those velocities before you subtract them. Otherwise, you'd be taking the square of the quantity, and now you have a polynomial, which is, well, let's not deal with that. So when we look at this here, if we were to put in some numbers, we know our force here is 220. We're looking for a delta x, and this is going to equal 1/2 the mass of our player, which was 62 kilograms, minus the final velocity squared, 1.2 squared, minus the initial velocity squared, 4.4 squared. Now, if we look at this real quick, we're going to see something a little strange. 1/2 is a positive number, 62 is a positive number because it's a mass, but 1.2 squared minus 4.4 squared, this is going to be a negative number here. Which means that whenever we eventually multiply everything together and divide by the 220, our delta x is going to be negative. Which, there's nothing wrong with thinking about that distance as being negative, but it's really not true in this case. What we need to recall is that these f and delta x, these were vectors, and they were dotted together. Which means that there is an extra cosine component right here. There is a cosine of some angle theta. And if we go back and look at our picture, we note that our displacement is to the left. There's our delta x. And our force, as we drew it, was to the right, which means that the angle between these two vectors was 180 degrees. When we go down and put 180 into our cosine of 180 is -1. So what we have here as we start putting in numbers is we're going to have our 220 times delta x, what we're looking for, times -1 from the cosine component, that's our cosine of 180, equals, and then let's put our numbers together on the right-hand side. Remember, like I said, square the 1.2 and the 4.4 before you subtract them. So 1.2 squared is 1.44. 4.4 squared is 19.36. 1.44 minus 19.36 equals -17.92 times 62 divided by a half. We get -555.52. Now, whenever we solve for delta x here, we see that the -1 and the negative here have divided out. They've canceled, so to speak. And then when we divide each side by the 220, the 220 goes away. Drop the 220 over here. And we find that delta x equals 555.52 divided by 220, which gives us just 2.53 meters. And that's how far away from the base our player started whenever they began their slide. And by the time they reached that base, they slowed down. So that's how we took this idea of work energy. It's really just one equation here, but we do need to be careful. This cosine component, because of the dot product that we've been talking about with our work equation, does come into play, and it is something to think about. But until next time, this problem is finished. Adios, and take it easy.